Assalamu alaikum. I am Muhammad Itarafin Hussain, and in today's lecture, I will be discussing about process management. Process management is a very important topic of operating system theory. In the previous lecture, as we have discussed about the operating system types, the services provided by the operating system, and the system architecture of the operating system, we have understood why do we need operating system and which tools we need actually to implement the operating system and how does our operating system actually work. We had got a simple overview, but in today's lecture we'll be exploring the working principle of the operating system in more details with process. So operating system uses process to implement its task efficiently. So in order to learn what is process, we need to first understand what does this system mean. This word means process. What does it mean by process? Well, let's dive backward and remember about the types of ways we have discussed earlier in the earlier lectures, and we have discussed about batch operating system, simple batch operating system, as well as multi-programming time shared operating systems. So in the batch operating system, we had jobs, and we kind of see that similar jobs were grouped in a batch in the batch operating system, and in time shared systems, we have noticed that one user can concurrently use multiple tasks at the same time. So uh, they're similar to process. So actually in textbook there is no difference between job and process. These two terms are the same actually. So what does it mean by process? So process is a program in execution. So literally a program that is in memory and that is being executed by the processor. So that can we can call a process. And for example, like we can take a program like Google Chrome, your browser. So this application uh, has many codes in it, and the portion of the code that is currently being executed, uh, that we can call process. So one program can have multiple processes running at the same time, but if you have single CPU based system, then your single processor actually can handle one process at a time. So but the speed of the process execution is so high that though it is executing one process at a time, you don't understand in human time. So to you, it is executing, everything at the same time. So to you, it looks absolutely fast. So well, we will see that uh, there is always a confusion between the word process and the word thread. So there are some differences between process and thread. So actually, a thread is a unit of execution within a process. So a thread will be within a process, and there can be multiple threads of a process. So there can be single thread of a process, or there can be multiple threads of a process. So they are the unit of execution of a process. So one process can have multiple threads executing for it. So suppose a game. So you are playing a game, and there are a lot of process going on in the game. But in a single process, suppose the process of visualizing the graphics of the game. So suppose you are playing a game which is like PUBG, so you can see around you with the graphical programming of that game. So there is lot of things going on around you. So someone is shooting at you, and suppose in your right side there are trees, and you have a gun. You can see a gun with in your hand. So this thing, there there are multiple threads which are actually in place to execute this process simultaneously. So there can be multiple threads of a process. So let's see it visually and practically. So let's open up the task manager of this operating system. Here, obviously, you can see my messy desktop interface. So don't look at it. It is so messy that you'll forget what you are looking for here. So let's try to look at the task manager of Windows. This is a default application of Windows. And here you can see that uh, here are many applications running currently in my operating system. And as you can see, there is one very popular app, Google Chrome. It is running on my background. And as you can notice, this Google Chrome has 28 processes with it. So this Google Chrome is a single application, but this single application has 28 processes. As you can see here from this task manager application, this single uh, browser has 28 processes along with it running. And like this another app, screen recorder, it has also three processes running along with it. So one application have many processes. And another thing, just to tell you, that Google Chrome is called memory eater for a reason. You can look at this, that it has occupied the most of the memories in my computer. This Google Chrome app along with itself, it has occupied around 40% memory, which is 16 GB. My PC has 16 GB of RAM, and Google Chrome alone has occupied around 40% of the memory. So it is a memory eater application, that's true, but we cannot live without it, right? Okay, so let me show you something else. This is another app called Process Explorer. If you can search in the Google, you can find it easily. And via this Process Explorer app, we are going to look at the processes too. You can see these processes are running in my computer. And let's find again our favorite Google Chrome. Here you can see the Google Chrome, and I have uh, minimized it, then expanded. Here we can see the same thing, that Google Chrome has multiple processes learning, but what is inside one process? So let's look at this process. Suppose this process. Here we can see that inside one particular process, here we can see inside one particular process, there are several threads running. So we can see that currently 7 threads are running for this particular one process. So Google Chrome is one singular application. It has many processes running along with it, and under each process we can see multiple threads. So I guess you are now clear now about this, that one application can have many processes and each process can have multiple threads. As you can see here in this Google Chrome, it has 7 threads running along with it. Okay, so I guess you have now a visual understanding and a better understanding of the differences between the process and the thread. So let's go forward. Well, here we can see in a process what is happening, and in a process there can be uh, the code of the program. Yes, so in a process there will be the code. The code is the main thing of the process. There will be the code, and then there will be the program counter and the registers. So program counter actually directs to the current instruction. So there are codes of the program. There are thousands and thousands of line of code in a program, and the program counter just indicates the instruction that is currently being executed. So program counter and the register stores the current activity too. So we have discussed about registers in the earlier lectures. We have stack, which stores the temporary data. We have the data section, which actually stores the global variable. We have heap, which actually provides dynamic allocation of memory during the runtime of the process. So, well, if I give you an example, like you want to write a code of making sum of 100 numbers. So you're writing a code that can take input from the users, and then it can sum it up, some 100 numbers at a time. So in that code you have the sum variable, which is the global variable which stores the sum value. So that is stored in the data section, and there can be temporary variables used to sum up the total sum. So that temporary variable will be stored in the stack. So we can see there are stack which can store the temporary data, the heap, and the data section, like the global variable sum, and the text. That this text part is actually the code. So the text section actually refers to the code. So we'll discuss about that a bit further in just a few minutes. We'll discuss about PCB, but before going to the PCB, process control block, we'll discuss about the process state. So there are multiple state of a process. So when a process executes, it changes the state. So state, you know, অবস্থা. So কিরকম এখন কোন অবস্থাটায় আছে. So we refers to the state as the current situation, the current situation of the process. So there can be several state of a process. The new state, when the process is being created, then we can say the process is in the new state. And the running state, when the process are in the CPU time, so they are being executed. So when the process is being executed by the CPU, by the processor, then we can say that the process is in running state. And the waiting, and if the process is waiting to get the CPU time, again we'll see that in a diagram. Then we can see, and if the process is waiting for IO time, then we can say that process is waiting and currently not running. There is the ready state of the process. So if the process is not yet uh, has a processes to be processed, it is ready, it is in the memory, but it is not yet has a processor. So it is not currently being executed, but it is loaded in the memory. Then we can say that the process in the ready state. And there is the terminated state. So when the process has finished its execution, then we can say the process in the terminated state. So this diagram will clear things up a little bit. So here you can see the states of the process. So the newly processed, so new, so when you are new, so as you can see earlier, the new state, actually the process is being created. So it is a very new process. Then a new process can go to the ready state. So when it is in the ready state, that means it is loaded in the memory and it is ready to be executed, but it is not yet being executed by the processor. Then after this scheduler dispatch, so this scheduler dispatch means you have got the processor. So the process gets the processor, then it goes to the running state. So you are in the memory, you are ready to be executed, you're not yet uh, uh, have the CPU to execute, but then you got the CPU, now you're in the running state. Then in the running state, several things can happen. You can have an interrupt. So from the running state, you can go back to the ready state to give, suppose to give priority to another um, to another process. So suppose there is another process who has better priority than you for getting the processor, for getting the CPU time. So that processors will be then given the CPU, and you will be no longer in the running state. You will be again into the ready state. You will be loaded into the memory, but again you will be out from the CPU time. When you get the CPU time again, then you will be in running state. So, and not only for this, the process can go to the waiting state if it is waiting for a event to occur. Suppose an IO event. So suppose your process is waiting for a keyboard press. Suppose your process is waiting for a keyboard press like yes or no, Y or N. So it will do something after you press the keys in your keyboard. Suppose a game. So then your process will be in a waiting state. It is waiting for an IO event, input output event to occur. Then after it has got the IO event completed, so after the IO event has completed, it will be go from the waiting state to the ready state again. Then it will uh, again wait for the CPU time. So when it gets the CPU time, it will be go to the running state again, and if it executes all the instruction it has, then it will go to the terminated state. So that is basically it regarding the process. uh, well, okay, so that was it about the process state. Now we can see the process control block. uh, the abbreviated version is PCB. So PCB has the process state. So as we can see as we have talked earlier about the process, that it has a program counter, stack, data, section, heap, as well as the code which is in the text section. Uh, every process has actually the process control block. So in the process control block, there is the process state, as we have discussed just previously, that there are several states of a process. Then there can be the process number. So every process have a particular identity to it. So that we can call the process number. The process has the program counter details, so the information regarding the program counter, and this information will be stored in the registers. So the program counter actually, it indicates to the instruction that is currently being executed. So you have a lot of code, and the program counter is actually indicating that particular instruction, that particular line of code, suppose, that is currently being executed. So the program counter actually uh, indicates to the currently executable instruction. So the instruction that is currently being executed, and the register stores all the information. And the memory, there are some other things in the PCB, the register, and it has the CPU scheduling information. Like we'll talk a lot about that in the future lectures, the CPU scheduling information, like how much time it will get from the CPU. So that kind of information. So the CPU scheduling is that a process will not run forever in the CPU. It will have limited time in the CPU. So the CPU scheduling information actually refers to that how much time your CPU has, your process has in the CPU. So how much CPU time your process has, then will be no longer it will no longer have the CPU. Then other processes will have the CPU. So the CPU information is regarding that. We will discuss that in the future lectures. There are the memory management information, the accounting information, like the process has the other details of the process, the IO status information. The process needs IO, and it needs some particular IOs. So that information is also allocated in the process control block. So this information regarding the process are stored in the process control block. Uh, well, the scheduling and the schedulers. So as I have just talked about this a bit earlier, that there can be CPU scheduling or job scheduling, whatever you can you like to say. There are two types of scheduling. One is long term. So long term scheduler, there are two type of scheduler and short term scheduler. So scheduler's main job is to schedule how much time a process will get. So the long-term scheduler selects which process should be brought into the ready queue. So there are actually two queues. So one is the ready queue, as you can see, and I will talk about it uh, in soon in details. And there are short-term scheduler which selects which process should be executed next and allocates CPU. So the schedulers is for the long-term scheduler bring processes in the ready queue, and the short-term scheduler decides which process should be executed next by the CPU. Okay, here we can see, as I have told you that I will be discussing about the ready queue. So ready queue is the processes that is in the memory right now and that is ready to be executed, that is in the ready state. So the processes that are in the ready state uh, are in the ready queue. So they are loaded into the memory. So suppose your process gets the CPU time, then after it gets the CPU time, so the short-term scheduler actually decides when it will get the CPU time. So when it has got the CPU time, then several things can happen. Suppose it can go to the waiting state and it can wait for the IO. So then if your process go to the IO waiting state, then in the waiting state for IO, then we can say that it is in the IO waiting queue. When it gets the IO, so it is done with its IO, then it will be back into the ready queue. And suppose there are other uh, process which are in the ready queue, and it is currently priority of the CPU to execute that process. So then your process will be swapped out of the CPU. So suppose your process is in the middle of execution, so it is not completely executed, but uh, another process which needs the CPU and it has the priority over your process, then it will take control of the CPU and your process will be swapped out of the CPU. And here you can see that it will be shared out here, which is partially executed swapped out processes. All the processes which are partially executed will be here, then it will be swapped in into the ready queue again. So your process is partially executed, it is not completely executed, but another process need the CPU, then your process will be swapped out and it will be swapped in the ready queue again. And in some time, after some time, it will get again the CPU. So this is the process actually. So the short-term scheduler is invoked very frequently, as you can see here in the diagram, that the short-term scheduler actually handles which process goes next to the CPU. So it actually handles which process will go next to the CPU. So it has to be invoked very frequently, that now you go, now you go, now you go. So it has to be invoked very frequently. And long-term scheduler invoked, it has to be invoked very frequently, but it may be slow. So it can be slow. So in the long-term scheduler, it loads all the processes in the memory. So it can be slow. So it can load all the processes at once. Then it can wait for some time for the new processes to be ready. Then it can load those new processes in the ready queue. So it has not to be, not too far. It has not equally to be fast like the like the short-term scheduler. So it is not needed for the long-term scheduler to be fast at the as the short-term scheduler. So processes can be described as either IO bound processes and CPU bound processes. So IO bound processes spends more time doing IO than computation. So your process can be IO bound, like suppose your program, but your driver program for your joystick. So suppose you have a joystick connected with your computer, and the joystick actually waits for your response. So it is more dependent on your IO response. So you are playing with your joystick. You're pressing switches, buttons of the joystick, and the program of the joystick actually waits for your intervention more than the CPU. So the program of the joystick, we can the processes of the joystick program can be called IO bound processes, and there are some processes which actually depends on the CPU mostly, rather than the programmer intervention. So those processes, we can call them CPU bound processes. There are some processes that doesn't even need the intervention of IO. So there can be some processes like the kernel. Okay. So process scheduling queues, as I have discussed, that there can be two main queues: job queue and ready queue. So job queue set all the processes in the system, and the ready queue set all the processes residing in the main memory. So ready queue actually the processes that are in the main memory. So that is the ready queue, and job queue is a set of all the processes that is in the system but not in the main memory currently. Okay. And device queue. So there can be a device queue. So suppose you need an IO device like keyboard. So many of the processes may need the same IO device. So suppose my Microsoft Word program as well as my game both need the same IO, which is keyboard. So there can be waiting for the IO too. So the processes that needs IO can wait in the device queue. Okay, so here we can see the representation of process scheduling with using the queue diagram. Okay, so the process that are in ready queue, that will have the CPU time, but it can then terminate. Suppose the all the instruction, all the course of the process, uh, and the computation of the process is done. So it can be terminated then. But if not terminated, the process can have a IO request. So suppose your process needs the IO, so it will then have the IO request, and then it will be in the device or in the IO queue. Then when it gets the IO, it will again go to the ready queue. Suppose your process is time slice. As I have told you before that the process is not does not have infinite amount of time with the processor, with the CPU. So your process will have sliced amount of time of CPU. So your process have sliced CPU time. So it will not have the processor or the CPU forever. So your process, suppose your time of the process is expired for the CPU, then it will go back to the ready queue and wait for the processor again, and it will have its time again. Then it will be executed for that much amount of time, that much slice of time. Then it will be when that time expired, then it will be again go to the ready queue. So your process may have child processes. Suppose from your process there can be other process called, so that is called fork a child. and that when that process executes, your process will go to the ready queue again. So um, that is regarding the child processes. Suppose your process is a parent process, and from your process, so your process is a parent process, from your process you need to execute another process, so that can be called as the child process. So when that process executes, your project your process goes to the ready queue. And another one, your process can wait for an interruption. Suppose your process is waiting for another process to take control. Suppose your process need that, so your process is waiting, so your process is waiting for another process to take control. So your process is waiting for an interrupt. Suppose um, let me give you an example. Suppose you're hungry, you are reading a book, so that is your process right now. So you're reading a book, and but you are hungry, so you are waiting for your mom, that your mom will call you to drink mango juice. So you're reading right now, but when your mom calls you, you just stop reading at that page, and then uh, you go to your mom for drinking your mango juice. That is called an interruption. That is called an interruption. So your mom called you for doing another process. So that process will take the CPU. Suppose then your human body is not actually involved into reading books rather than drinking the mango juice. Suppose you are now reading the suppose now you are drinking the mango juice, then you go back to your reading. So currently you are reading, you have the CPU, then your mom calls you for drinking mango juice, then interrupt occurs. So that call is an interrupt. So you will close your studies, and then you will another process like your drinking mango juice will take place. So it will have the CPU. Then after you are done with drinking mango juice, that process will be terminated, and you will start again with your studies. So your study will be in the ready queue, and then it will have the CPU whenever you resumes your study. So it will start from that point. Well, so that is actually what I have discussed right now. That is actually the context switching that we call theoretically is the context switching. When CPU switches to another process, the the system must save the state of the old process and load the saved data for the new process. So that is context switching. Actually, CPU switches one process to another process. So we can see uh, in the previous diagram, the in the queue of the process scheduling, that there are a lot of queues. So there are the IO queue. There are waiting interruptions for interrupt. So a process will be then in the ready section, then it will get the CPU, but for some reason, for this reason, for this reason, for this reason, or for this reason, it can be it can go to the waiting state again, and it can be in the ready queue again. So you know the context of the process actually switches. So CPU actually switches from one process to another process. So that is the context switching, when CPU switches from one process to another process. But for the switching, the system must save the state of the old process. As I have told, that you were reading a book, your mom called you for drinking the mango juice, but suppose you are reading the page number 351 of a book, then you just stop at that point. So you save the state of the old process, so you do not forget that you were in the page number 351 of your book. You do not forget that. Then you go to drink mango, so you load the save state for the new process. You go to drink mango, you finish drinking mango, so that process is that new process is now being terminated. Then you get back to your old process, and start reading for the from the page number 351. So you start and you resume that process. You do not start from the very new, the fresh state, but you resume that process. So that is context switching. Context switch time is overhead. Why it is overhead? Like when the context is switching, so one scheduler is like switching the context of the process, then the system actually uh, do nothing. So your context is switching at that very moment. Your CPU is sitting idle. When your context switching is happening, your CPU is idle. So that is a overhead. And well, let's see how does the context switching happen. So here you can see CPU switch from process to process. So how does this thing work actually? Suppose you have two process P0 and process P1, and suppose your process P0 is currently executing. You are reading your book, suppose. So one process is currently executing, and suppose you have the interrupt or the system call. So suppose you have we have discussed about system call. So suppose you have a interrupt or a system call, then you will save state into PCB. So your state information will be saved into the process control block. So as we have discussed earlier, the process control block has every information regarding the process. So that will be stored in the PCB, and then your process will be see this. Your information of the process is stored in the PCB. Then here reload state from PCB1. PCB1 is for the process 1. So you have stored your process P0 into its PCB. So you have the information stored of your process P0. Now after the interruption, you want to execute the process 1. So you will load the information of the new process 1, from its process control block. So we can see here PCB1. So you will load that information and start executing process P1. So here you can see process P1 is executing. Suppose then again you have an interrupt. Now this interrupt, after this interrupt, suppose you will now again uh, start executing process 0. So you have to save the process 1 first. So previously when we saved the state of the process 0, here we will have to save the state of the process 1, because currently it is running and you have again seen an interrupt. Then you will store the currently running processes state. So you will again save state of the running process is now process 1. So you will save the state of process 1 into its block. So you will save the state of process 1 is into its block, which is process control block 1. Then you will reload the PCB0. So we will reload again the information of process 0, which will be executed now. So process 0 will be start executing. So in this time, when you are switching the context, you are saving the information of process 1, and then you are reloading the information of process 0 to start executing the process. In the meantime, your CPU is sitting idle. So that's why I have called that the context switching is overhead. Similar things has happened here. So actually uh, you have saved the state of your running process 0. Then you are loading your running process 1 to be executed. In the meantime, your CPU is idle. That's why context switching is overhead. So that is all about today's lecture. We have seen, let's make a summary. of this lecture, we have seen the differences between, we have seen the definition of process and the differences between process and thread. Then we have discussed about the characteristics and properties of a process. So a process has program counter, stack, data section, heap. So in this diagram, you can see that. Then we have discussed about process state. So the state of the process is there. There can be mainly 5 state. We have discussed each of them. Then of course we have seen the diagram of the process state, how one process, the process goes from one state to another state, from one state to another state, how it goes. Then we have discussed about the process control block, where every information regarding the process is stored. uh, then we have seen about the schedulers. So process schedulers actually schedule the processes which has to be brought into the ready queue, which has to be given the CPU time. So short-term scheduler actually decides which process has to be given the CPU time. The long-term scheduler actually decides which process will be inserted into the ready queue. So we have seen that process executing in the CPU can be swapped out, and another process can start running, and after swapping out your running process, it will be again in the ready queue to be executed by the CPU again. It will be waiting in the ready queue. There are IO bound process and CPU bound processes. So we have seen actually three queues, important queues: job queue, which actually the set of all processes, and the ready queue, which have been loaded, which processes have been loaded into the memory to be executed. And there can be device queue, which processes are waiting for the IO devices that will be in the device queue. And we have seen the queue diagram of the processes. Then a process can have CPU time, then it can go to the ready queue for several reasons: for IO interruption, for time slice, its time has finished, for starting a child process, it can go into the ready queue, and of course for an interruption. So uh, suppose it has interruption from another process, then it will wait in the ready queue again to be executed. So then we have discussed about the context switching. So CPU switches from one process to another process. In the meantime, it has to wait for this context switching. So when you are switching from one process to another process, you have to sit idle for some time. So it is overheaded. That is the summary of this lecture. Hope you all will understand. And if you have any question, we'll see you in the live section. So be well, be good. Allah Hafiz.